back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And once again, in this hour, we're going to take your listener phone calls. Okay, moving right along now, let's take the first listener phone call.
Hey, this is Jared from New York, and I listen to you on the internet. I was wondering, do you think it's more possible that when we die, we just wake up as something else, even if it takes like 1 trillion years to be reborn? Or do you think we hop dimensions and our consciousness goes somewhere else? Thank you. Your show is great. You're great. Have a great day.
Well, the short answer is we don't know. We don't know what happens to consciousness when you die. However, science does say some things about what happens when we die. First of all, we have to have a definition of what is death because, well, the courts ask for that. Because if you're in a car accident, the question is, do you try to revive the people or not, given the fact that you need a definition for what is death? Now, some people would say that when the brain dies, then you die. For all intents and purposes, your brain doesn't function anymore, so you cannot respond to your loved ones, you cannot talk to anybody, and no one expects that you're going to come back from that state. However, your body may still function, because your body can exist independent of the brain. And so we have this gray area of what happens if you're in this situation where the brain dies, but the body keeps on going. And then we also have the near-death experiences that have sent many a bestseller onto the bestseller list, where people are in situations where they're half dead, half alive, and they see the light at the end of the tunnel. And they seem to be at peace. Well, science has tried to duplicate that effect. In fact, it was the United States Air Force who pioneered studies in this light at the end of the tunnel. You see, our jet pilots undergo maneuvers like turns which subject the human body to enormous G-forces where blood drains from the brain, goes into the body, and you could easily fall into unconsciousness as you black out. Now, the military is very worried about that because you're talking about losing pilots and, of course, losing multi-million-dollar jet airplanes if a pilot cannot come out of a bank correctly. And so the United States Air Force has a centrifuge, an ultracentrifuge where it puts pilots in and spins them around very rapidly and allows blood to drain from the brain to the point at which they're just at the level of losing consciousness. And what did they find? Much to their surprise, they found that GIs, just as they're about to lose consciousness in a very controlled situation, began to see a light at the end of the tunnel. They began to have a near-death experience. And this near-death experience was tunable. By tuning a dial, you could increase or decrease the velocity of the ultracentrifuge and actually create more of this effect or less of this effect. What the military found was when blood drains from the head, the eyes begin to lose blood as well. And blood from the eye basically drains from the outside in. That's how blood drains from the eyeball. You lose sight from the outside going toward the center. That means that you see a light at the end of the tunnel. So the light at the end of the tunnel is ordinary vision, such that you lose the peripheral vision gradually, leaving only the bright light at the very center. And so this was something that the military was very interested in, not for the sake of writing best-selling novels about coming back from the dead. No, they wanted to know at what point our jet pilots will undergo the process of becoming unconscious. And in the process, they found that the human brain will, in fact, create the light at the end of the tunnel. Now, you ask an even bigger question, and that is, well, where do we go after we die? And again, the short answer is we don't know. At the turn of the century, by the way, around 1900, many scientists believe that there are other dimensions beyond the 3 dimensions that we see around us, and that's where you go when you die. And so, believe it or not, there were scientists at that point, some of the best scientists of the Victorian era, in fact, who believed that death was really a motion into a higher dimension. Now, why do they say that? Because you see, back then, telescopes were looking for heaven. The church especially was very curious about finding heaven in outer space. But everywhere we looked with our telescopes, we could not find heaven. Now, this is very embarrassing for the church, because the church, of course, church doctrine, to a degree, depends upon heaven as a reward for good works, and yet we couldn't find heaven anywhere. And so, with our telescopes, we saw no evidence of heaven in the 3rd dimension. And so the clergy said, not all of them, but some of them said, maybe our souls go into hyperspace. Maybe our souls go into the 4th dimension, because if you are a 4-dimensional person, you would have superpowers, the powers of a ghost. You'd be able to walk through walls. You'd be able to disappear, reappear somewhere else. These are properties of higher dimensional beings that we cannot muster. Well, let's take another short commercial break, but after the break, we're going to talk about ghosts. Is it possible that our spirit can go into another dimension after we die? This, by the way, was a subject of considerable scientific investigation 100 years ago. Welcome back to Science Fantastic with Professor Michio Kaku. And Science Fantastic, we profile some of the most amazing developments in science and technology, and we are taking your listener phone calls. Well, before the break, we had a question that really pushes to the very brink of what is known about science and religion, and that is what happens when you die. Well, first of all, let me make very clear, I don't know. In fact, science deals with things that are reproducible, testable, and falsifiable. That is the bedrock of science. However, when we talk about things like, well, what happens when we die, we're talking about an area that is very difficult to measure and very difficult to reproduce or to falsify. You see, no one's ever come back from the dead. We've had near-death experiences, but no one has ever been totally dead and come back to talk about it and be investigated in a laboratory. And as a consequence, we scientists have very little to say about this. However, at the turn of the century, as I said before, Victorian physicists, some of the finest physicists of the era, in fact, some Nobel Prize winners, were actively engaged in researching the 4th dimension. The 4th dimension took the scientific world by storm around the year 1900. Many physicists thought that, well, if the universe can exist in 3 dimensions, why not a 4-dimensional world? And then they began to calculate the properties of a 4-dimensional being. You would be able to walk through walls. You'd be able to disappear, reappear. And who has these powers? Ghosts. And if you look back at the literature of 1900, the literature of Oscar Wilde, for example, they mentioned the 4th dimension in their plays, in their work. So the 4th dimension became the rage of the art world in the end of the last century. But what happened to all of that? Well, it all dissipated because there was no reliable information proving one way or the other the existence of these higher dimensions. Well, that's now changed because of something called string theory. String theory, we think, though we cannot yet prove, is the fabled theory of everything. There's even a Hollywood movie, The Theory of Everything, and it's about Stephen Hawking and string theory. So we do believe that there is a theory of everything, but it's not proven at the present time. So in other words, here we are. We believe that, yes, other dimensions can exist. But we can't prove it yet because our accelerators are not powerful enough to open up a gateway to these higher dimensions. And to answer the original question of the caller, what happens when you die? Well, the short answer is we don't know. It is not a measurable phenomenon. People have tried to measure it, but every time they've tried, they come up empty-handed. Okay, let's move on to the next listener phone call.
Hi, Michio. My name is David Riles from Detroit, Michigan. And my question is, could dark matter and dark energy be a parallel universe or a parallel reality to our own? Thank you.
Well, at first, your question sounds preposterous, but then again, there are some physicists who think that maybe you're onto something. First of all, what is dark matter? Dark matter is invisible matter, but it has gravity. That's how we know it's there. If it didn't have gravity and it's invisible, we wouldn't know it exists at all. But it has gravity. It holds the galaxy together. If it wasn't for dark matter, our Earth would have been flung into deep space billions of years ago. So what could possibly be invisible but have gravity? Well, one possibility, as you pointed out, is, let's say there's a parallel universe. A parallel universe where there is a star or galaxy hovering right above us. It would be invisible. Think of two sheets of paper. One sheet of paper right on top of the other, and you live on the bottom sheet of paper, but on the top sheet of paper there is another star or a galaxy. Now, gravity can go between universes because gravity is nothing but the bending of space. So gravity goes between these two sheets of paper. So you feel the effect of this star hovering over you, but it's invisible because light travels in your plane and in the other plane, but they never meet. And therefore you now have something which is invisible but has gravity. Bingo! That could be dark matter. And believe it or not, one of my colleagues, Professor Joe Licken at Fermilab outside Chicago, actually has written papers on the idea that maybe dark matter is nothing but ordinary matter hovering over us in another dimension. Now, this idea that you can hover over us in another dimension is actually not a new one at all. If you read H.G. Wells' novel, The Invisible Man, you realize how the Invisible Man became invisible. He was in a chemical accident, and that chemical accident threw him from our sheet of paper to another sheet of paper hovering over us so that he became invisible. His light traveled in his plane of existence and never intersected with our plane of existence, so we could never see him, but he was hovering right over us in a parallel universe. And so here we have an idea coming from science fiction, coming from H.G. Wells, which is being revived to explain the existence of dark matter. Now, however, let's be fair, what is the dominant theory of dark matter? The dominant theory of dark matter is that it consists of a new kind of subatomic particle. A subatomic particle that's invisible but has gravity. Now, so far, these are very rare, particles like that, but string theory does predict a particle which should have those properties, called the photino, the supersymmetric partner of light. The photino is invisible. It has no interaction with the electromagnetic field, and it has gravity. So, bingo, we now have a candidate for dark matter. Now, that doesn't mean that string theory is correct. That doesn't mean that dark matter consists of supersymmetric vibrations of a superstring. However, it does mean that one of the leading candidates for dark matter is that dark matter is nothing but a higher octave of a vibrating string. So we live in the lowest octave. Everything around us is music of vibrating particles and strings. But there are higher octaves, and dark matter could be a higher octave. Okay, well, let's move on. Take the next listener phone call.
The name is Lance Franklin. I'm from Christiansburg, Virginia. I listen occasionally on satellite radio. My question is with going towards the speed of light and quantum entanglement. What I wanted to know is if I synchronize, say, two communication devices through quantum entanglement and put one on a spaceship and send it approaching the speed of light, would we be able to communicate simultaneously? Thank you.
Okay, well, let me explain what quantum entanglement is and how Einstein was wrong on this question. First of all, Einstein hated the quantum theory. The quantum theory deals with probabilities, and he thought that the universe exists in a definite state, rather than being a sum over many possible parallel states. So he devised an experiment in 1935 to once and for all destroy the quantum theory. He said, let's take two electrons, put them together, and so they vibrate in unison, because in quantum mechanics, the electron has wave-like properties. Now separate them. If you separate them, an umbilical cord, an invisible umbilical cord, emerges connecting them, so they are connected to each other. If one electron spins up, this means the other electron spins down, so that the sum of the two is 0. Now separate these two electrons by a galaxy, 100,000 light years. If you jiggle one, then the other twin knows of the existence of its twin instantly. But that's faster than the speed of light, because you separated these two electrons by 100,000 light years. Bingo! Something went faster than light. So Einstein said, aha, quantum mechanics is wrong. But after the break, I'll explain how Einstein was wrong on this question. Sorry about that. Welcome back to Science Fantastic with Professor Michio Kaku. You can get on Science Fantastic by giving us a call at 612-564-8135. Well, before the break, we had a question about entanglement, so let me explain. In 1935, Einstein thought he created an experiment to demolish the quantum theory. So he said, if I have two electrons that are vibrating in unison, separate them, then I see that one electron is vibrating up in an upward direction. The other electron must vibrate down, conserving angular momentum. But that information traveled faster than light. And then Einstein said, gotcha, I gotcha. Because information traveled faster than the speed of light through this umbilical cord, faster than the speed of light, but according to relativity, nothing can go faster than the speed of light. Well, this experiment has been done, believe it or not. In a series of very famous experiments, we actually did the same experiment predicted by Einstein back in 1935. And guess what happened? Einstein was wrong. It turned out that information did go from point A to point B instantly, faster than the speed of light. So, Einstein was wrong. Sorry about that. But he gets the last laugh. Now, why is that? Because the information you get through entanglement is random information. It is information, but it's useless information. You cannot send Morse code. You cannot send the alphabet. You cannot send anything useful through the EPR experiment. The guys who proposed this experiment were Einstein, Podolsky, and Rosen. It's called the EPR experiment. And ironically enough, Einstein proposed the experiment to kill off relativity, but all it did was it proved that, well, Einstein was wrong on this question. Turns out quantum theory is correct. So the moral of the story is that, technically speaking, Einstein was wrong. Quantum mechanics rules. Every time we measure things at the atomic level, it turns out that, well, there are uncertainties. Einstein was wrong in this question. However, Some people think that we can communicate faster than the speed of light using entanglement, and the answer to that is no. For example, on Star Trek, you have to communicate with Star Trek headquarters at the other side of the galaxy, and therefore you have to be able to communicate faster than the speed of light. So in Star Trek, they invented something called subspace communication. And subspace communication allows you to go faster than the speed of light. Well, some people think that subspace communication is entanglement. Wrong. Entanglement allows you to send information that is useless faster than the speed of light. And so some things are simply not meant to be. Now, the only way that we know of sending information faster than the speed of light is not through entanglement at all. It's through a wormhole. Wormholes are, in fact, solutions of Einstein's equation. In fact, in 1935, the very same year when Einstein created the EPR experiment, in 1935, Einstein also came up with the idea of wormholes, which do allow you, in principle, to go faster than the speed of light. However, the energy necessary to build a wormhole is that of a black hole. Not for us. Sorry about that. Okay, well, let's move on now to the next listener phone call.
Hello, this is Frank from Columbus, Ohio. And my question is about black holes. We're constantly told that black holes have this mass that's so great, not even light can escape. But then you're told that there are jets that can shoot out from these black holes occasionally. And obviously they contradict one another. So how is that possible? Is it that, well, I'll let you answer the explanation. Thanks.
Okay, very good question. A lot of people have noticed the fact that whenever we have computer animation of a black hole, they show this gigantic swirling disk of gas with a north pole and a south pole of jets shooting out like a spinning top. However, it's also said that nothing can escape the gravitational grip of a black hole. So why do we have jets? You ask a very simple question with a very simple answer. And that is, surrounding a black hole, there is a small sphere, a sphere called the event horizon. If you fall through the sphere, then you die. It's a point of no return. So anything inside the sphere will inevitably be crushed by whatever is at the center of that sphere. However, if you have a glancing blow, if your rocket ship travels near the event horizon but misses it, then you can escape. So, where do these jets come from? These jets are falling gas that fall toward the black hole, swirl around the North Pole, and then get shot out the magnetic field through the North Pole, and they never reach the event horizon. That's the key. The two jets from the North Pole and the South Pole emitted from a black hole are outside the event horizon, because anything inside the event horizon will eventually get crushed. And so that answers your question. All the mass falling into a black hole that you see in a movie misses the event horizon, swirls around it, and then gets shot out the North Pole or the magnetic South Pole. I should also point out that Stephen Hawking abridged this picture a bit. He found that the black hole, that is the event horizon that surrounds the black hole, is actually gray. That it actually does emit some radiation called Hawking radiation. Nothing as spectacular as the two jets coming out from the North Pole and the South Pole, but it turns out that a black hole is actually hazy gray. It actually does emit some radiation because of quantum mechanics. Quantum mechanics says that everything is slightly uncertain. So blackness is a state of certainty, because you know there's nothing there. So blackness violates quantum mechanics. Therefore, it must be gray. And so Hawking showed it using the laws of quantum mechanics that black holes actually do emit some radiation, and that radiation is not the jets, it's an afterglow emitted from a black hole. Let's move on to the next listener phone call.
Hello, Dr. Kaku. My name is Juan. Question is, it seems that wherever there are a lot of atoms, such as stars and planets, there also seems to be gravity. Is there a way to test and see which of protons, electrons, and neutrons is the biggest determiner of gravity? Thanks. I look forward to your answer.
Okay, well, I didn't quite get the question, but I think what you're trying that is gravity and the subatomic particles we see around us, and how much does each contribute to the gravitational field that we see around us? Well, according to even Newton's theory, the amount of gravity that we see in the universe is proportional to the mass. And so if you want to know the relative contribution of gravity from the sun, the stars, the galaxy, the first thing you do is you calculate the mass of the object. Then you have to divide by the distance squared. So the farther an object is away, the less gravity there is. And so using these two effects, the fact that gravity is proportional to the mass of the star or the electron or the proton, but the farther away it is, the less gravity it is, bingo, you can calculate how much gravity there is in the universe. Okay, well, let's move right along and take the next listener phone call.
This is Jack Hickle calling from Anchorage, Alaska. I have two questions. One is, if the universe is ever expanding, and the universe is defined as all space and matter, isn't it true that there's only one universe and not multi-universes? If you're considering the universe to be, the beginning of a Big Bang theory with all the expanding galaxies going out from it, that being one universe. But if there's other Big Bangs in that same distant space where there's no matter at that time, that's still all one universe. There really couldn't be more than one universe. It could all be within a huge same void which goes on forever. That being said, if that one universe goes on forever and is infinitely large, isn't it also true that we could have something that's infinitely small, smaller than atoms and smaller than electrons? It just goes infinitely small, just like things go infinitely large. Those are my two questions. Thank you.
Well, you have some very deep philosophical questions there, so let's try to break them down. If there really is one universe, universe, that is one world, then you have a contradiction with gravity and with quantum mechanics and with cosmology. Because first of all, you have to deal with the creation of the universe itself. Where did that universe come from if it came from a small dot of some sort, a singularity? And second of all, you have to deal with quantum mechanics. Quantum mechanics says that everything exists in multiple states simultaneously. In other words, an electron could be spin up or spin down simultaneously. In fact, that gives us chemistry. If you look at chemistry and you wonder how is it that a spinning electron and a spinning proton can give us all this tremendous number of molecules and proteins and DNA and all of that just from a spinning electron and a spinning proton, the only way you can do that, the only way you can get the complexity of the universe as we see it, is because one electron can exist in multiple states simultaneously. Even though that boggles the imagination if you think about it, the fact that electrons exist in multiple realities, get used to it. That's called modern chemistry. Now, if you apply that to the universe, it means the universe must also exist in parallel states. In other words, once you quantize the universe, once you let the universe itself obey the laws of the quantum theory, then the universe must exist in parallel states, just like the electron exists in parallel states, and that's why we have laser beams. That's why we have transistors. Transistors and lasers defy common sense. By rights, they should not exist. If Isaac Newton were here, Isaac Newton would say, that's nonsense, that's junk. Lasers, transistors, they exist in parallel states, and that's impossible. Well, Newton would be wrong. Electrons, laser beams, photons do exist in parallel states, and that's why we have television. That's why we have radar. That's why we have all the wonders of modern technology. And so once we apply quantum mechanics to the universe, it necessarily forces us to admit the possibility of other universes, just like that forces us to investigate the possibilities of many electrons, which in turn give us modern chemistry. Modern chemistry is dependent upon electrons existing in many states simultaneously, and that's called a molecule. That's why we have molecules. And then you ask, what about the very small? Well, some people have postulated that maybe it goes on forever in terms of being small. You can have worlds inside worlds inside worlds, and it goes on forever. Universes inside an atom. Well, yes and no. It turns out that the laws of physics change when you go to different levels of reality. For example, if you're the size of a galaxy, you would see one set of physics. If you're the size of a planet, you would see another set of physics. And therefore, as you go to smaller and smaller scales, you do not create universes like our universe. Things become different. And at the atomic level, things become blurred and fuzzy. And so, again, in the quantum world, you do not simply get new worlds getting smaller and smaller and smaller. There's that movie starring Matt Damon where he's miniaturized and everything he sees around him is basically the same as it would be if he was large. Nope, doesn't work that way. The laws of physics change the smaller you get, such that when you enter the atomic realm, then everything becomes quantum mechanical. Nothing obeys common sense. Okay, let's move on to the next listener phone call.
My name is Jake Libby. I'm listening on KFQD. I'm in Wasilla, Alaska, and have a question about a satellite that I saw in the sky that it changed directions at what feels like a unlikely angle. And I have some friends up here that work for an aerospace company, and I have some retired NASA engineers, and they couldn't give me a good explanation. So since you talk about theoretical physics, I thought maybe you'd have an idea.
Well, first of all, without more information, I can't say either. However, I do think that the military could be experimenting with hypersonic drive, not supersonic, but hypersonic. And at that point, then perhaps you will be able to make U-turns and do gyrations that violate the ordinary laws of engineering. But until I get more information, I can't say. But yeah, the military is experimenting with hypersonic drive. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Okay, let's move on now. Let's take the next listener phone call.
Hi, Dr. Kaku. My name is Edward E. Mueller. I'm calling from Austin, Texas, and my question is the following. One of Dr. Stephen Hawking's last theoretical research paper talked about the possibility of other universes or a multiverse. What would be the possibility of traveling to other universes in the future with the right technology? Or is this simply out of the question? Thank you.
Well, first of all, you're right. My colleague Stephen Hawking did say that perhaps there are other universes out there, and perhaps one day we may be able to travel between these other universes. So let me explain. The leading theory of the Big Bang today is a modification called inflation. Inflation theory says, well, yeah, there was a Big Bang. The bang was much bigger than we thought. But bangs can happen all the time. So big bangs are happening even as we speak. The quantum theory says that if something happens once, it can happen again and again. So this means that there could be many parallel universes as our universe buds like a plant. Our universe buds other smaller universes. Then the next question is, obviously, can we visit these other universes? And that's where things get very complicated, because that requires a new theory of gravity. It turns out that Einstein in 1935 introduced the idea of a bridge that connects two universes together. So think of two sheets of paper that are parallel to each other. Take a pencil and ram these two universes together so that it's possible to start in one universe, climb up the pencil, and go to the other universe. That's called a wormhole, introduced by Einstein in 1935. It's called the Einstein-Rosen bridge. Einstein and his student Nathan Rosen had the idea that perhaps our universe is a bubble, and perhaps there could be a gateway between two bubbles connecting these two universes. Now, that sounds like a great idea, right? But if you get a sheet of paper and calculate what it would take, to go between these two universes, you find that the energy necessary to do that is comparable to a black hole. So in other words, it's not for us. We are too primitive. We can barely go to the moon. We can't even go to Mars with our astronauts. And so the idea that we can go through a parallel universe is for someone with supernatural or superhuman abilities. Now, there is a movie starring Matthew McConaughey called Interstellar. That movie was done with the guidance of physicists. One of them was Kip Thorne of Caltech, a colleague of mine. And I was curious. I'm a physicist. I know that it may be possible to visit a parallel universe, but the energy necessary to do that is comparable to a black hole. In other words, it would require a very advanced technology to do that. So I said to myself, how in the world is Matthew McConaughey going to be able to go through a black hole, through a gateway to a parallel universe in the movie Interstellar and still obey the known laws of physics? I was curious about that. Well, if you saw the movie, they get around that by saying that there's a mysterious alien civilization out there that gives us the gateway. They're the ones who create the gateway. We take advantage of it and therefore flee to another dimension. And at the end of the movie, they more or less hint at who these aliens are. These aliens that created the gateway to a parallel universe is us. They are our descendants. In other words, humanity, billions of years into the future, who knows when, took pity on their ancestors of the past, realizing that in the past their ancestors almost died because of this catastrophe, and the only way to save them is to give them the gateway from the future. Very clever. So in other words, it was our descendants from the future who did have enough energy to create a gateway for us to escape into a parallel universe. Very clever idea, because as I said, we can't do it. Maybe aliens from outer space have already done it, or maybe our descendants, billions of years from now, have already done it, and they took pity on us and gave us the gateway to save their past, which is, of course, our future. Clever. So let's move on and take the next listener phone call.
Hello, my name is Armand. I'm from Queens, and I listen to you on YouTube. I was wondering about your multiverse theory. So, like, when you make a decision, some people say that, like, your decision makes another universe bud or something. Is it possible that we just live in, like, one universe, our lives have only, like, one path? Like, doesn't really matter what choice we make, like, another universe won't bud off of that, but some people say there's parallel universes with us living in other universes and stuff. What do you believe? That there are other universes out there with us in them? That seems amazingly vast for that to be possible, but I mean, I'm sure it is possible. Have a great one. I love your show.
Okay, well, the short answer is we physicists are kind of confused on this question. Nobel Prize winners have debated this question for the last 50 years, in fact, going all the way back to the famous debates between Niels Bohr and Albert Einstein about this very same question. First of all, I teach quantum mechanics. I teach in the graduate program, and in fact, I wrote some of the textbooks, the basic textbooks on quantum mechanics, you can go to the library and check out my book, Introduction to Quantum Field Theory, which is for first and second year PhD students, and we have a whole discussion about this question. First of all, quantum mechanics is based on probabilities. The fact that we cannot calculate exactly if something will happen, we can calculate the probability that it will happen. So in other words, when you throw a rock in the air, Newton would say we can calculate exactly the trajectory of the rock as it moves in the air. That's what Newton would say. But in quantum mechanics, we say that, well, the rock could actually go through many parallel paths. And what we see with our eyeball is only an approximation, an average of many of these possibilities. So things are based on probabilities. So when you look in the mirror and you see yourself, you're not really looking at yourself as you really are. First of all, you're looking at yourself a billionth of a second ago, because that's what it takes for light to go from your face to the mirror and to your eyeball. So you're looking at yourself as you were. Then, according to quantum mechanics, you exist in many parallel states simultaneously, but they average to give you what you think is you. But if you wait long enough, some of these universes begin to bifurcate. So there's a certain probability that you'll walk off to the left, certain probability you'll walk off to the right, a certain probability that you'll wind up on Mars tomorrow, a certain probability that you will wind up on Jupiter day after tomorrow. Now, these are preposterous. These are alternate universes which are crazy. But in physics, there's a probability that you will wind up on Mars tomorrow. In fact, that's a homework question that we sometimes give our PhD students. Calculate the probability that when you fall asleep, you'll wind up on the other side of a brick wall, or you'll wind up on Mars. Now, this sounds crazy, but at the subatomic level, it happens all the time. At the subatomic level, that's what electrons do. They exist in multiple states. Now, Einstein, of course, thought this was horrible. This was a disaster, said Einstein. So he created, him and Schrödinger, an experiment to demolish quantum mechanics called the cat problem, the Schrödinger cat problem. You take a cat and put a cat in a box. Then next to the cat, you attach a gun. The gun is connected to a Geiger counter, which is connected to uranium. When the uranium atom fires, it sets off the gun, and the gun kills the cat. Okay? So far, so good. But you see, the uranium atom is a quantum mechanical object. Does it fire or not? It's a question of probabilities. You cannot know exactly when the uranium nucleus is going to disintegrate, setting off the gun. You can only calculate probabilities. Therefore, there's a probability that the cat will be alive because uranium never fired and the gun never fired. There's also a probability that the gun did fire and the cat is dead. So when I teach quantum mechanics, I say to my students, how do you tell if the cat is dead or alive? Well, you open the box. That determines whether the cat is dead or alive. But before you open the box, is the cat dead or alive? And you're not allowed to look. In quantum mechanics, you describe the cat as the sum of a dead cat and a live cat. Now, at this point, you may say to yourself, this is nuts. How can you add a dead cat to a live cat and get anything respectably honest? Well, that's how we do quantum mechanics. Sorry about that. This is called the many worlds theory. The idea that maybe the cat split in half, and so that in one universe the cat is dead, and the other universe the cat is alive. Now, does this mean that you can talk to dead people? Well, yes and no. Steve Weinberg, winner of the Nobel Prize, one of the greatest quantum physicists of the era, put it this way. Let's say you're in a living room and you're listening to the radio. You can listen to a radio station in Paris, in Moscow, in Havana, in Washington, D.C. Your radio can pick up shortwave from many different radio frequencies, but your radio is tuned to one frequency. That's why when you turn on the radio, you only hear one frequency. You got that? You exist in your bedroom simultaneously with many radio frequencies, but only of which you can hear one frequency. Now, let's turn on quantum mechanics. Electrons are a wave, and so there are lots of waves waving in your living room. There's the wave of dinosaurs, because maybe that asteroid never hit the Earth 65 million years ago. There's the wave function of pirates, because maybe the United States was not able to clear out the Barbary pirates and the pirates took over. There's the wave function of aliens, because maybe aliens visited the Earth millions of years ago. In other words, you coexist with many parallel universes right in your own living room. But your radio is tuned to one frequency. So you only see your living room. You don't see dinosaurs. You don't see aliens. You don't see pirates. Even though the vibrations of dinosaurs, the vibrations of pirates are still there. So why can't you talk to Elvis Presley? Elvis Presley died years ago, but his wave function could still be kicking around someplace. Why can't you talk to Elvis Presley? And the answer is very simple. Why can't you listen in on Radio Moscow? Because it's on a different frequency. We have decohered from Radio Havana. That's why you cannot hear Radio Havana on your radio. Your radio is tuned to one frequency, and it's not Radio Havana. This means that the reason why you cannot hear Elvis Presley in your living room, on a live Elvis Presley, is because we have decohered. We're no longer vibrating at the same frequency as Elvis Presley. So all this sounds crazy to you. You may think to yourself that, gee, the good professor has finally gone nuts. But this is called quantum mechanics. And that's how we build atomic bombs. That's how we build computers. That's how we build laser beams. Electrons existing in parallel states simultaneously. In other words, get used to it. Welcome back to Science Fantastic with Professor Michio Kaku. This hour is your hour. This is the time when you can send me an email or give us a call. Well, as I said before, not only are we taking listener phone calls, but we're also taking a lot of the emails that I get. One set of emails that I get is about, well, Bigfoot and Loch Ness Monster. And some people say, well, you can't rule it out, right? Maybe Loch Ness Monster does exist. Maybe there really is a Bigfoot out there. After all, we have reputable people claiming that they've seen Loch Ness Monster and they've seen Bigfoot. What do you say about mythical animals? Well, let me say flatly that I'm a scientist. Therefore, we are open. We are open to the possibility that, yes, there could be prehistoric animals that still walk the face of the earth. But because we are scientists, we start to make educated guesses and start to work on our hunches. For example, if there is a Loch Ness Monster out there, it probably had a mother and a father and a grandfather and a grandmother. In other words, there has to be a breeding population. You just can't have one Loch Ness Monster, because sooner or later it will die. That means you have to have a breeding population of several hundred. If I have several hundred Loch Ness Monsters, then there's enough there to create a self-sustaining colony of Loch Ness Monsters. But if there are several hundred Loch Ness Monsters out there, this means you should pick up the bones, the carcasses, the dinner that it ate. You should pick up remnants of the existence of the Loch Ness Monster. Because, as I said, one Loch Ness Monster will eventually die. And when we look for these things, we don't find anything. Now, submarines from scientists have been sent to explore the depth of Loch Ness. They found things that seem to indicate motion down there, which could be schools of fish or maybe the Loch Ness Monster itself. But they didn't see evidence of a breeding population. In other words, there should be baby Loch Ness Monsters. There should be bones of Loch Ness Monsters. There should be the carcasses of the lunch that the Loch Ness Monster found, and we don't see anything. Plus the fact that many of the so-called sightings of the Loch Ness Monsters have been proven to be hoaxes. So, what does it mean? It means that A, we scientists have to keep an open mind about these things. B, the evidence seems to be against the Loch Ness Monster, but hey, you never know. We have to keep an eye open for the possibility that maybe our theories are wrong. But at the present time, most scientists would think that if they were to gamble, they would bet that perhaps the Loch Ness Monster doesn't exist. Now, Bigfoot, on the other hand, is a little bit different, because we're not talking about sending a submarine to the bottom of the ocean. We're talking about remnants of fur and footprints, and we have to analyze them. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. Once again, I get a series of emails about mythical animals. Is it possible that we could have a Loch Ness Monster? Well, the answer is yes. However, we have to realize that the indicators are not there. In other words, there should be a breeding population of Loch Ness Monsters, maybe 100 of them, but we don't see bones. We don't see carcasses. We don't see any evidence of hundreds of Loch Ness Monsters creating a stable breeding population. Now, with Bigfoot, there are actually footprints and hair, fur left over from Bigfoot, and they have actually been analyzed by scientists. First of all, the fur has been genetically analyzed, and we find that it is the fur of the great bears. In other words, bears, large bears, give the impression that they are in fact Bigfoot, when actually they're nothing but large bears that leave behind fur. The fur has been analyzed on many occasions, and they are the fur of bears. Second of all, a few years ago, there were some children who had a press release, and they had a press conference. And they said that their father, who had just passed away, in his basement, had a whole collection of Bigfoot feet designed to create fake hoaxes and create the impression of footprints in the dirt. When the children went to the basement, they found a whole treasure trove of devices that allowed their father to create hoaxes. Now, they knew their father was a practical joker. They knew that because, after all, he was their father. However, the kids didn't realize that the father was not just hoaxing the neighborhood kids, but trying to hoax the world by deliberately creating fake footprints to create a Loch Ness Monster. Now, does that prove or disprove anything? No. It just proves that many of the footprints are, in fact, a byproduct of hoaxes. But you see, it is impossible to disprove a negative. By that, let me explain. Is it possible to disprove the existence of unicorns? And the answer is no. Because even if you search Africa and Australia, let's say, and you find no evidence of a unicorn, you can always say that, well, you didn't look hard enough. Perhaps there's a cave someplace. Perhaps there's an underground tunnel. Perhaps there's a world down there that we haven't yet explored in which unicorns exist. And that's the problem. You see, you cannot disprove a negative. So, can Bigfoot still survive? Can the Loch Ness Monster live? And the answer is yes. It's a possibility. Scientists would say the probability is very low for those reasons that I mentioned. But hey, look, we scientists have to keep an open mind because you never know. Chances are they don't exist, but maybe they do. Well, here's another question that I get in emails. It's kind of a silly question, but it does point to some rather deep physics. And that is, when you pull the plug on your bathtub or you pull the plug on a sink, which way does the water go down? counterclockwise or clockwise? Well, some people watching the evening news see pictures taken by satellites of gigantic hurricanes in the northern hemisphere, and which way do they spin? They always spin counterclockwise. But if you go to Australia and look at the weather patterns down there, the air currents spin clockwise. And therefore the question is, which way does the water go when you pull the plug on your sink or on your bathtub? Well, this, of course, is an experiment that you can do yourself, and what you find is rather inconclusive. What you find is that, yes, in principle, your drain should drain counterclockwise, just like a hurricane in the northern hemisphere. However, if with your finger you spin the water the other way, you can make it reverse directions. That's right. Water does not necessarily have to go down the drain counterclockwise. All we physicists say is that if you were to get a very still water that's very still inside your bathroom or inside your kitchen sink, and then you pull the plug very gently, chances are it'll go down counterclockwise. But you can force it. You can force it to go clockwise by spinning your finger. And then the next question is, why should it spin counterclockwise at all? After the break, we'll talk about your bathroom and which way does the water spin. Welcome back to Science Fantastic with Professor Michio Kaku. Before the break, we were talking about your bathtub. This is an experiment that you can do tonight, and the answer is very simple. When you pull the plug on your bathtub, chances are it'll go down counterclockwise, just like a hurricane. However, if you disturb it, you can make it go down the other way. In other words, this is called the Coriolis effect. It's a very small effect, and so you can nullify the Coriolis effect by spinning the water with your index finger and spinning your finger clockwise. But left to itself, left to its own devices, it will spin counterclockwise. Now why? Because the Earth spins. And when the Earth spins, it means that air rises and the Earth spins beneath it, causing air to spin in one direction. So in grade school, we learned that hot air rises. Why? Because hot air is less dense than cold air. Cold air is dense. Hot air is less dense because the atoms are in motion. Therefore, hot air rises. But when hot air rises, the Earth spins beneath you. So when the Earth spins beneath the air then spins in a preferred direction. And that's why we have the Coriolis effect. In fact, this Coriolis effect actually affected the British Navy. You see, when you shoot a cannonball in the northern hemisphere, the cannonball will swerve in a certain way because the Earth has moved during the flight of the cannonball. In fact, on the equator, you travel 1,000 miles an hour. That's right. 1,000 miles an hour, that's the velocity at which you're traveling on the equator. So the British Navy realized years and years ago, centuries ago, that when you fire a cannonball in the ocean, the Earth will spin beneath you, so you have to compensate. You have to compensate for the spin of the Earth. Now, here's the killer. Here's the killer. When the British Empire began to expand to Australia, to below the equator, the Coriolis effect is the opposite, beneath the equator. And therefore, all the British cannons fired the wrong way. Believe it or not, once a British gunboat went below the equator, all the calibrations of the cannonballs were done incorrectly. And so they had to redo the calculation. And so the British Navy had to ask physicists to calculate the Coriolis effect in Australia so that their cannonballs don't fly in the wrong direction. So here's a practical application of this effect that you can duplicate tonight in your bathtub by simply pulling the plug and seeing which way the water will go down. As I said, in general, it'll go down either way depending upon how you spin it. Left to its own devices in still water, it will go down counterclockwise. And why? Because of the Coriolis effect, because you are above the equator. And believe it or not, the Earth spins beneath you. as the Earth spins beneath the air, it affects the rising of the air because hot air rises, and that's why we have hurricanes. Okay, moving on. We have another set of questions concerning the speed of light. And the questions are, we now have so many experiments done on electrons, protons, subatomic particles. Does Einstein's theory still hold? Can you go faster than the speed of light? A few years ago, it was announced by physicists in Switzerland that you could go faster than the speed of light. So the question is, who's right? Can anything go faster than the speed of light? Well, the short answer is Einstein was right. A few years ago, an experiment was done with the atom smasher outside Geneva. They have neutrinos coming out of the atom smasher. Neutrinos were sent through a mountaintop because they don't react with matter that well, right through a mountaintop to go from Switzerland to Italy. And in Italy, they had a detector. So, by analyzing the speed of neutrinos going from Geneva to Italy, they calculated the velocity, and bingo, it was faster than the speed of light. Well, headlines were made. All of a sudden, headlines were saying Einstein was wrong. Neutrinos go faster than the speed of light. Oops, it turns out there was a mistake. Yes, there's always a mistake when you go up against Albert Einstein. Except on the quantum theory, Einstein's been right every single time. What happened was, it's a famous story. What happened was, the physicists had to calculate the distance from Switzerland to Italy. And how do they calculate that distance? Well, they use GPS, satellites, to calculate the distance between Switzerland and Germany. But the GPS uses relativity theory. So they were using relativity to try to destroy relativity. In other words, they were cheating. Sure enough, they had miscalibrated. They had miscalibrated the distance between Switzerland and Italy. Therefore, they got the wrong velocity for the neutrinos. When they redid the calculation, they found that neutrinos do in fact travel at light velocity or just below light velocity. Once again, Einstein wins out. But then, here's the other question. Can anything go faster than light? And the answer is yes, but these are not very useful. First of all, if I take a flashlight and I fling the flashlight from east to west, cutting across the entire night sky, and then I was to ask a simple question. How fast is the image moving as I swing a flashlight across the night sky? Well, believe it or not, the image goes faster than the speed of light. I mean, think about it. Your flashlight went from one side of the universe to the other side of the universe in a fraction of a second. Therefore, the image of the object as it swings across the night sky should go faster than the speed of light. So, why is Einstein still right? Because you see, the light particles, none of the light particles went faster than light. It was the image. But the image is not a tangible thing. The image is not made out of particles. It's the image. So once again, Einstein is right. The photons did not go faster than light. The image went faster than light. Once again, Einstein wins. Okay, well, that's it for Science Fantastic.